result, a complex function which is analytic is always differentiable, and a complex function which is differentiable is always continuous. But the converse need not always be true. That is, if it is given that the complex function f of z is continuous, it does not mean that the function is differentiable. Or if it is given that f of z is continuous, it does not always mean that the limit exists at every point. Let's look at an example. Prove that function f of z defined by f of z equals x cube into 1 plus I minus y cube into 1 minus I upon x square plus y square, where z not equals 0 and f of 0 equals 0 is continuous and CR equations are satisfied at origin, yet f dash of 0 does not exist. Here we are asked to prove that f of z is continuous. That is, we have to prove that f of z is continuous everywhere in the Argand plane or the complex plane. Also, we have to prove that CR equations are satisfied at origin. Still, f dash of 0 does not exist. That is, we check the existence of limit at 0, and if we obtain that the limit is not unique or the limit varies when we travel along different paths, we will have to conclude that f dash of 0 does not exist. To check for continuity of f of z or holding of CR equations, our first step will be to separate f of z to real and imaginary parts, because f of z equals u plus iv is continuous only if u and v are continuous. We separate f of z to real and imaginary parts by collecting terms independent of I and terms involving I. We obtain the real part u equals x cube minus y cube upon x square plus y square, and imaginary part v equals x cube plus y cube upon x square plus y square. Since it is given that z not equals 0, we have x not equals 0 and y not equals 0, because z is equal to 0 only when both x and y are simultaneously equal to 0. If z not equals 0, it means that x and y are simultaneously not equal to 0. Looking at the expressions of u and v, we can observe that u and v are rational functions and they have non-zero denominators. Hence, we can conclude that u and v are continuous at z not equals 0. Since u and v are continuous, we can conclude that f of z is a continuous function at z not equals 0. Now we have to check continuity of f of z at z equal to 0. Recall that to check whether f of z is continuous at a specified point z equals to z naught, we have to prove that limit z tends to z naught, f of z equals f of z naught. So in this question, we have to prove that limit z tends to the specified point 0, f of z equals f of 0. We change u and v to polar coordinates using the parametric equations x equals r cos theta and y equals r sin theta. We have the expressions of u and v transformed to u equals r times cos cube theta minus sin cube theta and v equals r times cos cube theta plus sin cube theta. We just substitute x equals r cos theta and y equals r sin theta in the general expression of u and v. After simplification, we obtain u equals r cos cube theta minus sin cube theta and v equals r cos cube theta plus sin cube theta. We have the equation z equals r times e raised to I theta. So z approaching 0 means that r approaches 0. We apply limit z tends to 0 over the function of u. That is, we have limit r tends to 0 applied over the expression of u, which is r times cos cube theta minus sin cube theta. We obtain the limit is 0, because when r becomes 0, the entire function assumes the value 0. Similarly, we have limit z tends to 0, v is also equal to 0, because the RHS assumes the limit r tends to 0, and the entire function vanishes. Thus, we have both u and v assuming 0 at the limit z approaching 0. Thus, we have f of z assumes 0 when limit z tends to 0. So, at z equal to 0, f of z is continuous. Since f of z is continuous at z equal to 0 and f of z is continuous everywhere at z not equal to 0 also, we can conclude that f of z is continuous everywhere in the Argand plane, or f of z is continuous for all values of z in the complex plane. Now we check whether CR equations are satisfied at origin. We use the limit definition of partial derivatives. We evaluate dou u by dou x, treating y as a constant, and the constant value to be assumed by y will be 0. We have the expression dou u by dou x equals limit x tends to 0, u of x0 minus u of 0 divided by the increment given to the x, which is x here. limit x tends to 0, x minus 0 divided by x equals 1, because we substitute x equal to x and y equal to 0 in the general expression of u we have obtained, and we obtain u of x0 equals x and u of 0 equals 0. We apply the values and we get limit x tends to 0, u of x0 minus u of 0 by x equals 1. Similarly, we have dou u by dou y, treating x as a constant, where the constant value for x will be 0. We have limit y tends to 0, u of 0y minus u of 0 upon the increment given to the y, which is y itself here. We substitute x equal to 0 and y equal to y in the general expression of u. We obtain the answer as minus y, and u of 0 is again 0. Thus, we obtain the limit as minus 1. Similarly, we have dou v by dou x equals 1 and dou v by dou y equals 1 depending on the general expression of v. Note that CR equations are valid here at origin because dou u by dou x equals dou v by dou y and dou u by dou y equals minus dou v by dou x. Hence, at 0, CR equations are satisfied. We evaluate f dash of 0 using the limit definition. We have f dash of 0 equals limit z tends to 0 f of z minus f of 0 upon z. We have the standard expression of f of z given in the question. For z, we make use of the expression x plus iy, and f of 0 is 0. And when z is approaching 0 along the path y equals x, we have f dash of 0 given by limit x tends to 0, 0 plus 2i x cube upon 2x cube into 1 plus i. We obtain this expression by just substituting y equals to x in this expression. After simplification, we obtain the answer as I by 1 plus I. We rationalize, that is, we multiply numerator and denominator of this expression using 1 minus I, and we obtain the answer as I times 1 minus I upon 2. Here we multiply I inside and we get the final expression as 1 plus I divided by 2. Now, z is approaching 0 along another path, that is along x-axis, which has the equation y equals 0. We just substitute y equals 0 in the limit and we obtain f dash of 0 equals limit x tends to 0, x cube plus I x cube divided by x cube. After simplification, we obtain the answer as 1 plus I. When we follow different paths, we are obtaining different values for the limit. So, the limit is not unique, and hence we will conclude that f dash of 0 does not exist. So by this problem we conclude that even if f of z is continuous everywhere in the Argand plane, there is a point which is 0 here at which f of z is not differentiable because f dash of 0 does not exist.